Okay, so the key things to note with our continuous random variables is that our probability in actual fact is an area under the curve. So just in the example here, if this histogram represents the weights of people, okay, well then the probability of someone being 83 kilos, which is really someone being between 82.5 and 83.5 kilos, is really this area of that rectangle divided by the total area of the graph. All right. So what our continuous distribution does, it turns the area under the graph into a value of 1. So if this total area here is 1, the probability then simply becomes whatever the value is of the rectangle that we're looking at. And from our previous knowledge, we know that the area under a graph can be determined by the integral. Okay, so in short, if I want someone to be 83 kilos, or it's like finding someone to be between 82.5 and 83.5 kilos, and so it's the integral between those two limits of whatever the rule for the function happens to be. All right, so in general, we can come up with the concept that for any continuous random variable with a probability density function, so it has to be a probability density function, the probability of getting someone between A and B is just given by the area under the curve. All right, and we know the area under the curve is the integral between A and B f of x dx. All right, so a couple of key things. The most important one there is the area under the curve of the whole function between the complete limits of the graph has to be 1. All right, so that's a proviso. All right, so we spoke. If we have a look at the example here, we've got a probability density function of f of x equaling 4x on 18. So if I just do a quick sketch of that, well, it's a straight line graph with a gradient. And if the x value is 3, because that's the limit, the y value, if I put x equal to 3 in there, I get 4 by 3, which is 12 on 18. So 12 on 18, which we could simplify, obviously, but I'll leave it there. So that's the y value. So we know the area is a half base height, which is a half times 3 times the height, which is 12 on 18, which is a half of 36 on 18, which is equal to 1. So by definition then, that function there is a probability density function. So if I wanted to work out the probability of someone, of the value being between 2 and 3, I just work out that area there, which is the integral between 2 and 3 of whatever f of x happens to be. All right, let's look at examples. I guess something just to refresh our memory, if we've got a definite integral that's got an upper limit that's not defined, or it's not finite, we can on our cas just substitute infinity in. We can put infinity into the cas and it'll come up for us, but technically speaking, we should be talking about limits, okay? What happens to the function as k gets really big or as k gets really small, all right? So again, if we have a probability density function, the function will always be greater than or equal to 0. There can't be the graph can't go under the x-axis because that would give me a negative area, hence a negative probability or a negative value. And the limit of the function between negative infinity to infinity always has to be 1. So let's go over a couple of these examples. All right. So find the value of k that makes this a probability density function. Okay, so if it's a probability density function, it means that the integral between 0 and 3 of whatever the function is has to equal 1. All right, so that's the definition of a probability density function. All right, so that means then add to the power, divide by the power, evaluated between 3 and 0 has to equal 1. So I get k times 3 squared on 2 minus 0 is equal to 1. Therefore, we get 9k on 2 is equal to 1. So k is equal to 2 on 9. Right? And hence, if I want to find the probability that x is greater than the 2.1, that means from 2.1 to 3 of 2 on 9 x dx is the probability that x is greater than 2.1. Clearly, something like that would be done on our CAS. And using our CAS, we get an answer of 51 on 100, which is obviously 0.51. So that's probably having a value greater than 2.1. Just really, again, emphasize it doesn't matter whether it's a greater than or equal to. Okay, the endpoint is still 2.1. So the inequality signs in our continuous is not relevant. Example 2. Sketch the graph of f of x equaling. So let's just sketch the graph over here first. If x is greater than 0, so if x is less than 0, the function is 0. So that's just that blue line there. And if x is greater than 0, it's a negative exponential, which looks a little bit like that. And if x is 0, that makes that a third. So there's my function there. There's x, and that's f of x. All right. Show that f is a probability density function, which means that we need to show that the integral between 0 to infinity, put the third out the front, of e to the minus x on 3 dx is equal to 1. So if I just put that straight into the CAS, you will get 1. But let's show it manually using the proper notation. Okay, so that implies then, now we can't just substitute infinity in. So that means it implies that the limit as k approaches infinity of this whole rule, and instead of putting infinity there, I'm going to put k. Okay, so then I get the limit as k approaches infinity of 1/3 -1 on 1/3 e to the minus x on 3 between k and 0, which is equal to the limit as k approaches infinity of 1/3 of, well, first 1 over -1/3 is -3. Put k in, I get e to the minus k on 3. And if I substitute 0 in, I get minus -3. Put 0 in, e to the 0, which is equal to the limit as k approaches infinity of -3 e to the minus k on 3 plus 3. Now, and we can see from the graph, as k approaches infinity, this function here gets closer to 0. So it's equal to the limit, oops, so we've done the limit, which is just equal to 0 plus 3. Oops, I've got the third out the front, which is equal to 1. All right, so yes, you can put it straight into the CAS because the CAS is clever enough to calculate the infinity symbol, but mathematically, if we have to show it, we really should be using limits, okay? So now, if we go to our practical solving, if x represents the length of time between the interval, the time between customers at an auto bank, all right? Probability that more than 7 minutes elapses. So the probability that x is greater than or greater than or equal to 7 is equal to the integral, or more than 7 to who knows how long, of 1/3 e to the minus x on 3 dx. So on our CAS, we can see that that's equal to 0.09697, so 0.0970, okay? Again, if we had to do it by hand, we probably should use the limit notation, but we've got our calculator available. So D, the probability that more than 10 minutes elapses between successive customers given that more than 7 minutes has passed. So what does that mean? So it's the probability that X is greater than or equal to 10 given 7 has passed already. So using our formula, it's X has got to be greater than or equal to 10 and X is greater than or equal to 7 over probability that X is greater than or equal to 7. So what interval satisfies the top line? What numbers are greater than 10 and greater than 7? Well, clearly it's just the numbers that are greater than or equal to 10. And the probability that X is greater than or equal to 7 is already worked out for us. So now I just got to work out X is greater than 10. So that's equal to 0.0, well, the top line is equal to 0.03567. So my final answer is 0.3679. So the probability of having to wait more than 10 minutes, given you've already waited 7, is 0.3679. Okay, so it's really just the way in which we work out our probabilities that is different, not necessarily the types of questions that are asked. Okay, so let's have a look at our next example. So we've got a probability. Sketch the graph of F to begin with. So let's come over here and sketch the graph. Notice how really only focus on the top right side, because that's normally, well, having said that, we've got a little bit of a left. So the graph is equal to 0.2 between -1 and 0. So that line there is there. So that's -1, that's 0, that's 0.2. All right. And then we have a straight line given by 0.2 plus 1.2x between 0 and 1. So we'll maybe call that 1 there. So it's going to look a bit like that. Then it says it's 0 everywhere else. So it's 0 back this way if x is less than -1, and it's 0 this way if x is greater than 1. All right. Probably should find out this point up here. So if I put x equal to 1 into here, I get 1.2 plus 0.2. So it's the 0.1, 1.4. Okay, so there's my probability function graph. Find the probability that x is between -0.5 and 0.5. So what am I looking for? I'm looking for from there at -0.5 to +0.5. So I need that area there and that area there. So clearly I'm going to have to split my integral up because I've got two different rules. Now, I can actually work out this first area here in two ways because it's just the area of a rectangle. So let's set it up formally. So I need to find out, so the probability of being -half less than x, which is less than a half, is equal to the probability of being from, let's rub that out. It's equal to the integral from -1/2 to 0 of the function that I'm interested, 0.2 dx, plus the integral from 0 to +1/2 of 0.2 plus 1.2 dx. All right, so they're the two sections. So this first section there is actually just a rectangle. So that's 0.2 tall, 0.5 wide, isn't it? But so I reckon I should get 0.01 if I use my CAS. If I use my CAS, I'll get 0.2 by 0.5, which is equal to 1/10 or 0.01. And if I work that out as well, I could do it manually, but if I use my calculator, I get 1/4. So what is 1/10 plus 1/4? Let's make them both over 20. 2 over 20 plus 5 over 20, which is 7 on 20, which is equal to 0.35. Okay, so in summation, getting the probabilities from this point here, setting up the question so you're working out the interval that you want to solve over is the same regardless of whether it's conditional, whether it's continuous or discrete. It's just this section here that's different. Okay, so if you have to work out a probability in a continuous distribution, you have to work out an integral. All right.